Good morning, everybody. We're gonna get this show started just in a minute. I just need to do a last second audio check just to make sure everything's okay. I accidentally stopped the stream and I'm just restarting it. Good morning, everybody. Okay, I can hear myself. That's good. Perfect. I can hear myself. Let's get this show on the road. Turn this down just a little bit. Alrighty. So, good morning, everybody. Welcome to this third part of our mechanical design tutorial. I need to move my screens. I want that up there and this down here. Yeah, that's way better. Sorry. Give me one moment. This can go. This can go here. All right. So, welcome to part 3 of our mechanical design tutorial. Thank you for sticking around this long if you've made it this far. So, today we're going to be focusing a lot on finishing our designing for manufacturing, talking about what manufacturing options we have, um, and what special constraints and things we should consider while we're putting this together. So, without further ado, let's get right into it. So, I'm sure you all remember this. We went over this design last time. This is the design I did before we started this tutorial series. So what we're going to do today is we're going to see how I got to a gearbox plate that looks like this. We're going to do this back plate, this back tube, this back plate. These arms are already done, so we're not going to redo them. This gusset also, these are all trivial parts. Um, Especially if you stuck with us through this. So I'm not going to do these. I have these already finished in an assembly. We're just going to reuse them. I'm going to talk a little bit why I made choices for the parts I used up here and why it's necessary. Um, and then do some final stuff like design some spacers, tell you where you can get bolts and stuff. Finalize these shafts because this is a part that we have to manufacture this shaft. Um, and then really, I'll be letting you guys go. So let's get right into it. So as you all remember, this is the gearbox plate we finished last class. We finished extruding it into the third dimension. So this is our final 3D part. A few things we like to do in general when we're manufacturing stuff, especially if we're going to send it out for manufacturing, if we're going to do it on the CNC, is typically we want to round off the corners. We want to make it look nice. And we want to make it like aesthetically pleasing for no particular reason other than just taking pride in the work that we're doing. Um, and also keep in mind we're doing so the goal is to manufacture this on a CNC or water jet it. So we can do funnier shapes with the water jet or the CNC. We don't have to worry about having to be able to manufacture those shapes on our own. Sorry. Um, so for example, I can do things like fillet all of these corners at like a quarter inch or half an inch, like really big fillets. I'm actually going to do these two corners separate than the other corners because these are going to have nicer, like they're going to have more gradual bends, so I'm probably going to have to put a larger fillet on these. Something like this probably. On the other three corners, I'm going to do probably a slightly smaller fillet because that fillet would end up being really huge. See, you can see it's massive fillet. Yeah, I'm not a fan of how big that is. So let's see what 20 looks like. 20 looks much better. So let's do 20 millimeter fillet. And you can see this is already looking way better. It looks more cleaner. It looks more finished. Um, Now there are some main differences here that we're not going to do that you're going to see that you saw in my other design. For example, I cut out this area here. Why did I cut out this area here? Oh my god. Oh, sorry. Um, Really, this is just for looks. Uh, On projects like our rover or on other projects that weight matters, you would do this to save weight. And in this project, weight doesn't matter. This is going to get mounted to the goalie frame, so we don't care how big or heavy it is. We are using actually very thick aluminum plate for both of these parts. So really, we're not too concerned for weight. If we were concerned for weight, we could cut that area out and make it look cool, but we don't need to for this. This is more than fine. So I'm actually going to save this, and we're going to move on to the next part, which is the guy on the back. I can't close this because there's some important stuff here. Like these dimensions are all important for us. So I'm going to keep this, or actually what I'm going to do, I'm going to use the handy dandy snipping tool if it ever decides to open. There it is. Just so I don't have to keep opening this design back up, I can just do this. Now I have the dimensions. I'm going to put it on my other monitor. And then I'm going to start a new part. Okay, so we're going to do the little plate that goes on the back. I'm going to do these parts really fast. Oh, part of my yawning. For some reason, I can't get over that. Okay. Holy. So, 2 inches. Lengthwise, doesn't matter yet. Same. Okay. So I'm going to do the exact same bolt hole sizes and dimension it the exact same way we did the other one. So 6 millimeters, 20 mil gap. I'm going to pattern it 3 times and then do a measurement from the other side. So 3 by 20 mils, not 200 mils, 20 mils. Does that look right? That looks a little small. We're going to check that. $26.52. How did it get to that number? That's weird. I don't know how to edit sketch entity, this type of sketch entity, so I'm just going to delete them and redraw them. Let's do a linear pattern. There's also not... So we've made a few mistakes here, actually. Or I've made a mistake here. This and this need to be coincident. This... Let's go for 30. Do 2 of these like that. And then you and you. Needs to be 20, actually. And I bet you that's what's changing this size. Yep. Um, okay, so let's do this then. Leave driven, leave driven, and then now I can do hmm. It's weird. SolidWorks being weird. I'm gonna leave it the way it is, and we'll just live with it. 13 millimeters is not that weird of a dimension. So there we go. There's our holes. Let's go to this. It was 30 millimeters between, so let's do that. 20. 1, 2, 3. And we're gonna have 3 of them. This was 13. Like this. And then our bearing, we can measure that. I gotta go back to the drawing because it's not a sketch dimension. So our distance, I'm just gonna insert some extra dimensions in here. So this distance here is 45.92. That's a weird number, but it's fine. We're doing this on a CNC, so it doesn't matter too much. No, cancel. I don't want to close. 45.92. 45.92, 1.125 millimeter hole. This is the bearing hole, if you remember. Not millimeters. 1.152 inches. There we go. And then this plate is nothing special. It's really just these parts. So all I'm going to do is I'm going to draw a rectangle around it all. And that's going to end up being majority of this part. So I'm just going to dimension this so that we have a little bit of wall, not a lot of wall. 30 is probably a little bit big. Let's do 25. Yeah, like that. Exit. Let's extrude into the third dimension. So 1, 2. And then 0.5 inch. Not 0.5, 0.25 inch. These are 1/4 inch plate. I'm going to round off the corners as well with a 20 millimeter fillet. And there we go. There's the other side of the arm. So we're going to call this the in-class rear shoulder. Okay, I don't need that open. I can close this. I'm gonna stop this. Discard and save. All right, so we've done the front, we've done the back. Yes, save all. Let's do the tube. Then we can put it together with the rest of the stuff. So the tubes are really easy to do. Basically from the top down, we're gonna do a sketch on the top plane. We're gonna do a center rectangle. That's gonna be 2 inches by 2 inches, and then we're gonna do a an offset basically. So 2 inches by 2 inches. I'm going to do offset entities to the inside, and then for the 2-inch tube, we are assuming to have, I believe, 1/8 of an inch walls, like this. Does that make sense? No, sorry, 1/4 inch walls. So 0.25 inch, like this. That way, the center distance, so in here, um, ends up being about inch and a half, which is the same size as the frame that is used to make up the goalie, like his skeleton. So we can extrude this now. No. And I'm gonna extrude for 6 inches. If we need to, we can make it larger. Okay. Now first, we need to put some holes on this guy. So these are gonna be the mounting holes to mount to the frame. So I'm gonna just do a center line. And these are also gonna be 6 millimeters. And I'm gonna do them 20 away from here. And then we're gonna do a sketch pattern. Let's do 30. And then we'll make this bigger. Okay, so there's the holes. Now I can just extrude them through all. And there we go. Now I'm going to make this taller. Make it 8 inches because then our bolts are going to end up colliding with each other, which is not ideal. So I'm just going to make it taller to save us from that hassle. Okay, now I need to do basically the same thing on this side for our gearbox plates. So sketch on this face. This time I'm going to start at the bottom and go up. Just like that. I'm going to extrude a cut all the way through. Again, we're going to do through all. And there we go. There's the tube. So I'm going to save this as the in-class shoulder tube. And now we can start assembling. So I'm going to start a new assembly. New assembly. Okay. And we can start putting our parts together. So I'm going to pin this here. I'm going to browse. So I want this. Like that. Since these are the same, it's really symmetric. Or not symmetric. It's like the same but rotated on the two sides. It really doesn't matter which side goes where. This, and then last but not least, the other side, like that. Okay. Now I'm going to do some mates just to put everybody together. So I'm going to mate you this face to this face so that they are touching. This hole to this hole so that they're aligned. And then I'm going to do a second hole so that they stay aligned. I could do the bottom, but I'd rather just do the holes. Like I could do this face to this face, but I'd rather just use the holes. It really doesn't make a difference though. So if I do just these concentric mates to keep it in place, if I do 2 concentric mates, that's more than enough to keep it in place. It won't stop it from moving off the face. Like if you think about it like in a real world aspect, think about it as putting a bolt through the hole. Um, if you have a huge bolt, it won't stop it from moving off the face. That's why we have to do another constraint, which is equivalent to like putting a nut and clamping it. However, it will stop it from like rotating and stuff. Treat mates like real world constraints and stuff. Like if you do a mate, think of it like especially like a concentric mate or something. Think of it like putting a bolt through something. If you're gonna do a coincident like face to face mate with a concentric mate like this too, think about like putting the nut on the bolt and then tightening it down. Um, You want to treat SolidWorks like you're building the thing in real life, because then it'll also make building the thing in real life more straightforward. Now I already have the gearbox and the bearings already downloaded, so I'm gonna add these things into the design. Half-inch hex bearing. I want two. Actually, while I'm here, let me just pin this. Give me the other hex bearing. Put it over there. I want the gearbox while I'm here. I believe it is this one. That's not a gearbox. So you can see it's kind of like, remember how I said we don't want to rotate it like this? We're gonna use uh mates to fix that, but it's really not an issue. Like we could rotate it there when we bring the part in, but we're just gonna use mates to fix it. So if I take this hole and I make it concentric to this hole, and then all I have to do is I gotta take a round feature here and make it concentric to this here. Oh, is that not gonna work? I don't think it wants to play nice. I don't know if I did them. I know for a fact I didn't do the dimensions perfect, but it should line up. So let's see why it's not lining up. I wonder if I can use this middle hole. Also, some of these parts don't, like, the parts look completely round and stuff, but when SolidWorks does the feature recognition, it doesn't want to recognize it properly. Yeah, that's kind of a pain. That's fine. We'll do that. And that's good enough. Yeah, you can see it's not perfectly centered. That's why it doesn't want to line up concentric. Honestly, it's fine. We know that in the real world that lines up. Okay, so let's put these bearings in place. So I'm using the flange. Oops, that's not the right face. I'm going to use this flange to basically keep the bearing from moving off this face or through the plate. And to do that, basically on the shaft, to stop it from coming off in the other direction, on the shaft, we're going to use spacers, acetal spacers, so plastic spacers, and we're going to drill and tap the shaft. So basically you tighten a bolt into the shaft and that's going to stop this bearing. It's basically going to compress everything onto the shaft and stop the bearing from coming off the shaft. So we will probably make those spacers in a minute. Actually, you know what? Yeah, we'll make them in a minute. So I'm gonna show you guys where we can find bolts and stuff for like this design. So really quick, I need to understand how long it is so I can buy appropriate hardware. So we're looking at 65, call it 65 millimeters from side to side. So we're probably gonna go for a 70 millimeter bolt. So let's go to McMaster Car. The reason we're going to McMaster Car for the bolts is because fasteners are cheap on McMaster Car, and these are the fasteners we purchase because we buy them in bulk. I'm gonna stick to socket head because I like socket head. I want metric. I want M6. You can see it gives me options for the thread pitch. I'm just gonna let it tell me which thread pitch I need for my length. So yeah, 1 millimeter. Um, let's do the partially threaded black oxide. And oh, this is new. Usually you have to go into the part and like look at the fancy. Yep, we're gonna do 3D step. We're gonna download. I'm gonna save. Now I need to open up my file explorer just to move it into the correct location. Documents. Is it on desktop? Here it is. Okay, now bear with me for a second. I have to do like feature recognition for this, so I gotta open it as a step. So when you get step files, SolidWorks is not going to treat it like a normal part, although it technically is. It has to do feature recognition, basically to understand what it's looking at. Do I want to do diagnostics? Yeah. And see this line actually? See it? See this line right there? This is what I meant by usually it separates around parts. It's kind of annoying that it won't treat it as a whole round part, but it's kind of hard for it to recognize it as a perfectly like circular part, but it's fine. I'm going to leave it as the default name. That way, if I ever have to go purchase it, the part number is in the name. Okay. So let's do assembly. Let's do insert. And I'm going to insert a handful of these. So 1, 2, 3. Okay. And let's just put them in place. Now, you see it's not sticking out a ton. I could have threaded that other plate because it's thick enough to allow for a thread. Um, I chose not to just because putting a nut on the end is easier. It's also easier to manufacture. Um, and that's really the only reason. If I wanted it to be lighter weight, I would not put a nut, and I would just thread this plate here with like the appropriate thread for these bolts. But honestly, it's okay. And like I mentioned before, we're not trying to save weight on this design. Otherwise, I'd have a pocket here to remove material. So it should be perfectly fine. I'm not going to include the nuts just because like I know that nuts have to go on the end here. Um, and this is really just for demonstration purposes. Um, okay, so let's do the arm. Let's put the arm in. So I have that part already fabricated, like I have an assembly for it. Now, a few things. What are these guys at the end of my arm? These are called Versa hubs. So these are offered by Vex. They are like part of their Versa series. So I'll show you. We're using specifically this one. This is aluminum construction, so it's like aluminum alloy. I think it's like 6061 probably. And basically it's got a 1/2 inch hex bore in the middle. That's what this is. And this allows us to attach things to shafts so that they will spin with the shaft. So this basically allows power to be transmitted into our arm. It's held on by these 6 bolts. They have a specific bolt circle. That's what is like drawn in here. And really that's all there is to it. We're gonna do basically just a coincident mate to line these holes up. And then we're gonna do a width mate. So for those of you that are newer to SolidWorks, in the advanced mate, you can do something called a width mate that is gonna put the part that you want to mate between 2 faces. So watch, I can do select this face and select this face, and then I want to select this face and this face, and it's going to center it for me between these two. And I need to choose, so it's made this hole, this face and this face coincident. I need to make now this face and this face also coincident, and it should line up properly, just like that. See? Now, obviously, we need some spacers in here. We're going to go over that in a little bit. Everything else I already have fabricated, so I trust that you guys should be able to do these parts on your own. For example, this shaft is just a half-inch, um, half-inch hexagon. It's nothing special. I think it's 6 inches long. Um, you guys should be able to do these parts on your own. They're very, very straightforward. Now, why does this have a hole in the end? I mentioned that we are going to put a bolt on the end to compress everything to the shaft so that the bearings don't move. So basically, I'll show you what that looks like. So we expect that this face is going to be flush, and then we put a bearing and not a bearing, a bolt and washer on here. So this hole is going to get tapped for, like, let's say M4 or M5. We put a bolt and a washer, and we tighten it up so that it's pressing on the bearing. And that's going to stop the bearing from moving past that bolt. Now, if we do that on both sides with a bunch of spacers in between, there's no room for anything to move. So there's no room for the bearings to move. There's no room for the arm to move. And then everything stays constrained in their positions. So I'm going to put the pulleys and everything on, and then I'm going to show you the spacers that I'm speaking of. So I'm going to, oops. So let's go like this. I think it's the 24 tooth. Yeah. Okay. And then the mates are, again, the same mates that you did for the arm. It's just here to here, here to here, and then that's a wrap for that. And then here to here, and here to here. And then I'm just going to make these two coincident. That way they can move together. And I'm going to dimension them a specific different distance. So I'm going to put you and you a specific distance away. And let's do like 10 millimeters in the other direction. Like that. There we go. And we're also going to need spacers up here, by the way. So let me take some measurements. So we're going to need a handful of spacers. So let's do some evaluating. So the distance from here to here is 9.5 millimeters. I can round off that 0.3. It's fine. If it's got a little bit of play, it's okay. Also, if it's too tight, nothing, like, it'll bind. So I need two of these. What distance in here? 10.4. Okay, let's do 10. And then this side is also 10. Yeah, let's just do 10 and 10. The reason I'm saying let's do 10 and 10, we can always make this shaft shorter, just like the smallest amount shorter, because we're manufacturing it. 12, and then let's call that 8. Okay, and also these spacers could be oversized also, and then bolts have like length, right? Since we're gonna put a washer in the bolt, if it's oversized, the bolt will just have to like thread in, and there will be a bit of a gap, which is really not an issue. Um, oops. Okay, so I'm gonna only do a handful of these. I'm gonna do the ones that go down here. The ones up here are the same and they're trivial. So let's do quick sketch here, top down. Uh, 0.5 of an inch. And then I'm gonna say 3/4 inch acetal, so 0.75 inch. Acetal is like plastic. I think it's PV. No, it's acetal, uh, which would be like PVA. I don't know. It's not PVC, but it's kind of it's similar composition. It machine's really nice. It's really easy to manufacture with. We use it a lot. We've used it for shafts before. We've used it for spacers before. Uh, we use it for a bunch of stuff. It's really, really good material to work with. So I do need 10 millimeters. Okay, I gotta do another one. I could get away with using the 10 millimeter in the spots where I need the 9.5. But like I said, again, it's gonna be really, really tight in there. So, like, I'd prefer not to. And these are just really quick and easy. So you do them one at a time. It's really not too bad. Okay, let me just close. Okay, let's start inserting those spacers. So I need one of these. I need two of these actually. One, two. Now I need the 10 millimeter. One, two, and then we'll live with that for now. Okay. There we go. And then this face, this face, to this face. Done. You can see it's like nice and in there. Uh-oh. That's less than ideal. It's kind of hard to mate these when they're like when they want to automatically go into the hole because you can't see them. Like right now, this is gonna be a pain. Because I can't see into that part. So I'm gonna kill that mate, move it out, and then do the mate again. Clear. I could also just do these as concentric mates to the pulley. It doesn't matter too much because I know where they belong and where they need to live. And I know that they're going to fit on the shaft, but I want them to spin with the shaft in the case that I like want to spin the design. I just want it to work proper. So that's the main reason I'm doing it improper, like fully. Wonderful. Now you can see, look how small that gap is. That's that zero point 0.5 of a millimeter I rounded off, or zero point 0.4 of a millimeter. It's really fine. Like I said, we can make the shaft the slightest bit smaller. They usually get manufactured undersized anyways, just by like chance. So it's really not an issue. Oh, no, clear. I'm just gonna do this and this, concentric, coincident, and there you go. So this is what I meant. Now, if we put a bearing and a bolt and a nut on here to press down on that spacer, nothing is going to move anywhere because we have a bolt and nut, a bolt and spacer, a bolt and washer on this side, pushing it to the one side, a bolt and washer on the other side, pushing it in the other direction. Everything's going to be squeezed together. The bearings aren't moving anywhere. The arm's not moving anywhere. The pulley's not moving anywhere. Everybody is happy. Everything is good. And the same goes for up here. We would make those other two washers, those other two spacers, clamp them on there with a bolt, and then it's off to the races. And really, that's all that there is to this design. There's not too much more. So there's a little bit that I want to talk about, like design for manufacturing and what options we have available to us and what considerations we need to take. But beyond that, that's really all it takes to design something like this. It's pretty straightforward, to be honest. So I'm gonna save this up really quick. This is the in-class assembly. Awesome. So DFM, what is design for manufacturing? So you need to design with the means of manufacturing in mind. So means of manufacturing, what machine am I going to use to make this part? I need to make a shaft like this one. I'd end up using a lathe. I know for a fact I'm going to use a lathe to make this part. I can't do it on the CNC. I could cut it, just it comes in stock, like big pieces of stock. I could cut it down to size. It comes as the hex shaft, by the way. It comes as the extruded half-inch hex. Um, and then we cut it to size and we put it on the lathe and machine it down to exact dimensions. I couldn't just cut this to size because I got to put these holes in it. And I need to tap it. So this is going to see the lathe. These acetyl spacers, I know these are going to see the lathe. I can't do them any other way. What else? What else? This plate I mentioned earlier. I want this plate to be manufactured on the CNC. So what considerations do I need to take? CNCs have minimum radiuses they can cut, minimum internal radiuses. So for example, see something like this. If I don't have an end mill, the end mill is like the tool that the CNC uses, like the little tool that you put in the collet that spins and cuts. They call those end mills. The end mill has a minimum radius, which is the radius of the tool. And that is the minimum radius that it can cut. So if you have a 1/4 inch end mill, the smallest it can cut, that's 1/4 inch diameter. The smallest it can cut is a 1/8 of an inch, and that would be the radius, right? If you have an 1/8 of an inch end mill, the smallest it could cut would be like a 1/16 of an inch, so on and so forth. So that means like this radius in here, or this diameter also from like here to here, needs to be bigger than my end mill. So you saw in my other design, in this one, I had these pockets, right? I manufactured these with CNC in mind. This is a 1/4 inch radius. 1/8 inch radius, which means that I could manufacture this on a CNC. That being said, this could also be water jet, meaning the internal radius doesn't matter because water jet can do much smaller internal radiuses to basically to the point where it doesn't matter too much. Because water jet is just like a stream of water. Um, There's also other stuff. So with the CNC and the water jet, you need to consider tolerance. The water jet is going to have a higher tolerance than the CNC. CNC can do parts more accurately. The water jet is going to struggle to do those parts super accurately. That being said, if you need to do something like this, it's way more than accurate enough. Like dimensionally, the only thing that needs to be super accurate here is like the size, not even the size of these holes, because they can be drilled out with by hand. So you would design them smaller in the CAD, and then you would take a hand drill with the appropriate drill bit, and you would just clean them out and drill them out. What's really important is the distances between the two pulleys, and that's it. And the water jet will have no issue doing that. Neither will the CNC. Those holes will be perfectly tolerant to each other. What you got to worry about actually is the radius and the diameter, the specific dimensions of that hole. They on the water jet, they will not be exact. They will probably be undersized by about a millimeter. So you might have to take it over to the mill and clean out the hole, or take a file to it and clean out the hole, which is always a bit of a pain. Whereas with the CNC, those holes are going to be near perfect. What else? This plate, this is easily done on the bandsaw and with the drill press. We would do this on the bandsaw and the drill press. Basically, what we would do is we would take the 2D layout of this plate, print it out on a piece of paper, glue it to a sheet of aluminum. So this is really thin aluminum. This is like 1/8 aluminum. We would glue it to the sheet of aluminum, take it over to the bandsaw. The bandsaw is kind of like, for those of you that don't know, pull up a picture. This is the bandsaw. It's like a big rotating blade. It's really good for cutting flat stuff. So we would cut this out on the bandsaw. We would glue it on, and basically we would just trace it out. And even the bolt holes, these holes are not super important. If they're like off a little bit, you just go bigger and you put a washer, and then it's fine. Um, so even the holes, we would just put the image, like we would print the image on the photo that we're gonna glue to it, and we would just drill the holes on the drill press. And the same for these tubes. These tubes would get cut on the horizontal bandsaw. Horizontal bandsaw looks like the normal bandsaw, except your material is stationary and the bandsaw slowly moves down and cuts it. It's good for cutting stuff like tubes and shafts before they need to be cut to final dimension. And like most of these parts would probably either get done like the holes with a hand drill, or just on the the drill press. This bearing hole would have to get done on the mill. So we have a tool specific for this. I think I've mentioned this before. We have a end mill, specific for the bearing size. The bearing sizes are a little bit smaller than, a little bit bigger than the hub size, but that's perfectly fine because we want this to be clearance. We don't want this to be interference where the hub is touching the material of the tube. We want it to be a little bit bigger on the inside hole there. Um, and then yeah, there's this guy up here. Again, this is like another job for the mill. Um, and really, I had all of this in mind as I was manufacturing this, as I was designing this. I know that these parts got to get manufactured in a certain way, so it's important that you keep this stuff in mind while you're doing it. Beyond that, I don't see too much else. Let me think. If there's any last second stuff. No. Oh, the only thing, if we find that this is not enough to stop the whole assembly from rattling around, like if the bolts are not doing a good enough job holding it in place, which they should, we'd probably just 3D print it into it. Like a little sock that goes between the tube, the round tube and the square tube, and that should be way more than enough to keep it in place. Beyond that, I really think that's all. Um, yeah, I think that's everything. Yeah, yeah, that's everything. You can see actually. So remember how I said I wanted it so that it works? The pulley moves properly with the arm as you move it, which is really nice and ideal. And if you want, you can check. So we can also check. I'll check right now, but I know it's not going to hit. At any point, it does not hit. See, I can go even into the goalie and it still doesn't hit. And the frame is gonna stop the tube before it hits the gearbox. Actually, see, this is more what we want as opposed to the arm hitting the gearbox to stop. See, this plus this arm is also gonna hit the goalie in the head before it hits that gearbox. Now, we talked about this last time in gearbox placement and stuff. Um, all right, yeah, I don't got anything else to be honest. Yeah. So one of my mods just put in the chat. Yeah, we're if you're looking forward to if you want a way to improve your SolidWorks skills, we're gonna be running some SolidWorks tutorials, and we are hosting a SolidWorks certification course in the summer. So stick around for that. Thank you for coming, everybody. Appreciate you guys sticking through these tutorials. Um, yeah. Uh, have a good day, everybody, and yeah, that's really it. Uh, yeah, I had fun doing these guys, and hopefully I will see you guys in more of these tutorials. If not, it's been a good time, and I'll talk to everyone.